проверю, все ли я правильно сделал. Ну, вроде есть. Да. Говорите, еще кто-то подойдет, да? Ну, не знаю, будем ждать, не будем. Ну ладно, давайте я немножко для начала просто напомню издалека. Okay, at the previous lecture we introduced the functor k0 for unital rings. So let's briefly recall the main steps of the construction. So we start with a unital ring R, a unital ring, and we consider the set denoted by V of R. This is the set of isomorphism classes of finitely generated projective R modules. Finitely generated projective R modules. By default, we consider left modules. This is not essential, in fact, but this is our choice. And we define, well, first of all, we observe that V of R is not just a set. It's an abelian semigroup with respect to the following operation. If we have two elements of this set, that is equivalence isomorphism classes of projective modules P and Q, then we define the sum of these classes to be the equivalence class of the direct sum, P plus Q. And this operation makes this set into an abelian semigroup. And now we define the group K0 of R to be the Grothendieck group, of the semigroup V of R. Well, I will not repeat now all the steps of the construction of this group. Very roughly, this is an abelian group, a universal abelian group containing V of R. In fact, this is not exactly true, because in the general case, K0, V of R is not contained in K0 of R, but in the general case we have a canonical map, a canonical semigroup homomorphism from V of R to K0 of R, which is universal for homomorphisms from V of R to abelian groups, in the sense that for any homomorphism from V of R to an abelian group G, there is a unique group homomorphism, which makes the diagram commutative. So this is K0 of R. Today our first goal will be to relate this construction to topological K-theory developed by Atiyah and Hirzebruch. A relation to topological K-theory. Oh, by the way, coming back to this picture, well, I've already said that in the general case, this map, this canonical map, is not injective. And actually, we know when it is injective. It is injective if and only if this semigroup is cancellative. And in terms of modules, this means precisely that two finitely generated projective modules are stably isomorphic if and only if they are isomorphic. So by definition, two modules are stably isomorphic if they become isomorphic after adding a suitable free direct summand. So if we have this property, if any two stably isomorphic modules are isomorphic, then this map is actually an embedding, and V of R is cancellative. Okay, so today we discuss a relation of this construction to topological K-theory. Topological K-theory is defined in terms of vector bundles over topological spaces. So to begin with, let's recall what vector bundles are. So we start with a topological space X, and we give the following preliminary definition. By definition, a vector quasi-bundle over X is a pair consisting of a topological space E is a topological space and a continuous map P from E to X. Together with a vector space structure on every fiber, with a finite dimensional vector space. And here we assume that all vector spaces are over the complex numbers, a finite dimensional complex vector space on space structure on each fiber. And the fiber is just the preimage of a point under P. And that's all. So roughly, a quasi-bundle is just a family of vector spaces Ex spread over a topological space together with the topology on their disjoint union E. Well, this notion is very general, and it's not very interesting. Actually, we are interested in special class of quasi-bundles, which are called vector bundles. And before defining them, let's introduce morphisms between quasi-bundles. Suppose we have two quasi-bundles. Well, sometimes we denote them by little Greek letters. So suppose we have two quasi-bundles, xi and eta, over X. A morphism, we define a morphism from psi to eta to be a continuous map. A morphism is a continuous map f from E to F, such that, first of all, it respects fibers, or equivalently, the following diagram commutes. So this is P, this is Q, and this is F, such that the diagram commutes, and such that F is linear on each fiber, such that the restriction of F to Ex, well, it automatically takes Ex to Fx by the commutativity of the diagram. So we want this map to be linear. It's linear. So clearly the class of all vector quasi-bundles over X forms a category. Let's denote it like this. This is the category of quasi-bundles over X. Let's now look at a simple but important example. Take a finite dimensional vector space V. By default, we equip V with a standard topology. The standard topology of a finite dimensional vector space. By standard topology, I mean the topology determined by any norm on V. We know that any two norms are equivalent. So they generate the same topology, and this is the standard topology of a finite dimensional vector space. So we now let E be just the product of X by V, and we define the projection P, as denoted by P1. This is just the projection of E onto X. So it takes every pair XV to X. And then it's clear that we obtain a quasi-bundle, a vector quasi-bundle over X. So every fiber of this quasi-bundle is isomorphic to V. And by definition, we say that a vector quasi-bundle psi over X is trivial if it is isomorphic in this category, if it is isomorphic to a quasi-bundle of this form. If it is isomorphic to this product quasi-bundle for a suitable finite dimensional vector space V. Now the objects we want to define, that are these vector bundles, are those quasi-bundles which satisfy this condition locally. To say this more in a more correct way, let's introduce some notation. If we have a subset Y of X equipped with the induced topology, and if we have a vector quasi-bundle psi over X, then we can restrict it to Y as follows. We define the restriction of psi to Y to be the following pair. We take the preimage of Y under P. This is a subset in E. And we restrict P to this subset. And this is easily seen to be quasi-bundle over Y. And we call it the restriction of psi to Y. And now we have the following definition. Again, suppose that we have a vector quasi-bundle psi over X. And we say that it is a vector bundle. Векторное расслоение in Russian. If for every point of X there is a neighborhood U of X such that the restriction of psi to U is trivial. Trivial over U, of course, it is defined over U. Okay. Well, let's also introduce some terminology. If we have a vector bundle psi over X, then we say that X is the base of this bundle psi, and E is called the total space. The total space of psi. Well, clearly, vector bundles form a category. They form a full subcategory of the category of vector quasi-bundles. Let's denote this subcategory like this. This is the category of vector bundles over X. So it is a full subcategory. In other words, the morphisms are defined in exactly the same way as for quasi-bundles. Okay, let's now discuss sections of vector bundles. So if we have a vector bundle xi, well, maybe before we discuss sections, let's look at some operations on vector bundles. Actually, there are many useful canonical constructions on vector bundles, but we will need only two of them. The first construction is called the Whitney sum of two vector bundles. Here we have two vector bundles xi and eta, fq, two vector bundles over x. Then we define their Whitney sum, the Whitney sum, psi plus eta. This will be also a vector bundle over x. And it is defined as follows. Its total space is the fibered product of E and F over x, together with a natural projection onto x, defined as follows. So the fibered product of E and F is by definition the set of those pairs u, v, in the product, such that p of u equals q of v. And the projection R takes every pair uv to p of u, or equivalently to q of v, because they are equal. So this is easily seen to be a quasi-bundle over x. The fiber of this quasi-bundle at every point is just the direct sum of the fibers, ex plus fx. And it's a simple exercise to show that this is indeed a vector bundle. That is, if xi and eta are locally trivial, then the Whitney sum is also locally trivial. The second construction that we will need is the pullback of a vector bundle along a continuous map. So suppose we have a continuous map between two topological spaces, x and y, continuous map, and a vector bundle xi over y. Then we define the pullback of xi along f to be a vector bundle over x. So xi was over y, and the pullback will be over x, as follows. Its total space is often denoted by f star of E, and as a topological space, this is again the fibered product of x and E over y, together with the projection onto x. So P1 takes every pair x v to x. Again, this is easily seen to be a vector quasi-bundle over x, and its fiber over every point is isomorphic to the fiber of E over f of x. So we simply take, from the point of view of fibers, we simply take every fiber of xi over y and pull it back to x. So the fibers, these two fibers are the same. And the topology is defined as the induced topology from the product. So this is a vector quasi-bundle, and again, it's a simple exercise to show that it is also locally trivial, so it is actually a vector bundle over X. Okay, let's now discuss sections of vector bundles. Here we have a vector bundle psi over X. Then, by definition, a section of psi is a continuous map S from the base to the total space, such that the composition of P and S is the identity map of X. In other words, this is just a continuous map which takes every point in the base to a certain point in the fiber over this point. The set of all sections of Xi is usually denoted by gamma of Xi or by gamma of Xe. This is the set of all sections of Xi. Well, actually, this is not just a set. The set is a vector space, and moreover, it is a module over the algebra of continuous functions on X. So let's make some simple observations. First of all, gamma of Xe is a C of X module with respect to the following natural operations. If we have two sections S and T, and a continuous function A on X, then we define the sum of these sections. We define the sum pointwise. That is, S plus T of X is S of X plus T of X. Here we use the fact that each fiber has a vector space structure. And similarly, we multiply by A pointwise. We define the section A AS by the following simple formula. And this, again, will be a section of the same bundle. So the set of all sections becomes a C of X module. Moreover, this module depends naturally on E in the following sense. If we have a morphism, F, of vector bundles, offers both vector bundles, from E to F, then it introduces a homomorphism of the modules of sections, gamma of Xe to gamma of Xf, just by composing every section with F. So it takes every section S to the composition of F and S. So let's look at the picture. If we have two bundles, PQ and morphism F, so it makes this diagram commute. If we have a section S of E, we can simply compose it with F. First apply S and then F, and we get a section of Q. So this is a well-defined map, and it is easily seen to be a modular homomorphism. Gamma of F is C of X module morphism. So we see that gamma is actually a functor from the category of vector bundles over X to the category of C of X modules. Moreover, it's easily seen that this functor commutes with products, or more exactly with finite direct sums. So it takes the direct sum of the Whitney sum of two vector bundles to the direct sum of the respective modules of sections. This is a simple exercise. The equivalent of this functor is additive. Okay. Let's also look at the following simple proposition, which describes modules of sections of trivial bundles and morphisms between trivial bundles. First of all, if we have two finite dimensional vector spaces, V and W, finite dimensional vector spaces, then first of all, there is an isomorphism, more exactly a C of X module isomorphism, between the module of continuous functions on X with values in V, so this is a C of X module in the natural way, and the module of sections of the respective trivial bundle, X cross V. And this isomorphism looks as follows. If, say, f is a continuous function with x on X with values in V, then the corresponding section S takes every point X to X to the pair X f of X. And this is easily seen to be a one-to-one correspondence and actually a C of X module isomorphism. And second, if we are interested in the set of all morphisms from one trivial bundle to another trivial bundle, then there is again well, formally it is bijection, a bijection between the set of all continuous maps from X to the set of all linear operators from V to W. Well, this set is by default equipped with, again, with the standard topology of a finite dimensional vector space. So all these spaces are finite dimensional. So this space is isomorphic to a space of bundle homomorphisms from the trivial bundle X cross V to the trivial bundle X cross W. And it is given by the following formula. If F is a continuous map from here to here, then the respective bundle homomorphism, well, that's denoted by F tilde, is given by the following formula. It takes every pair XV to the following pair. We have X in the first place, naturally, because it is a bundle homomorphism. And here we apply the operator f of X to the vector V. And again, it's easy to see that this is actually a bijection. In fact, we can observe that actually statement 1 is a special case of 2 because of the following remark. This is actually a very simple exercise. Let theta 1 denote the one-dimensional trivial bundle over X. Then for every bundle, every vector bundle psi over X, the set of all bundle homomorphisms from theta 1 to psi is naturally isomorphic to gamma of psi. And by using this isomorphism, we can observe that actually part 1 of this proposition is a special case of 2. Okay. Okay, from now on we assume, so far X was an arbitrary topological space, but from now on we assume that it is compact and Hausdorff. Assume that X is compact and Hausdorff. We denote by V of X the set of isomorphism classes of vector bundles over X. And just like in the case of projective modules, this set is an abelian semigroup with respect to the following operation. You have two isomorphism classes of vector bundles psi and eta. Then we define the sum of these classes to be the equivalence class of the Whitney sum of psi and eta. And it's easily seen that under this operation, V of X becomes an abelian semigroup. And we now define the group K0 of X to be the Grothendieck group of V of X. So this is an abelian group naturally associated to X. Why do I say naturally? Well, it is indeed natural in X. It is a functor because of the following simple observation. If we have a continuous map f from X to Y, where X and Y are two compact Hausdorff topological spaces, then we have a semigroup homomorphism V of F, which acts from V of Y to V of X, and it is defined as follows. It takes every the isomorphism class of a vector bundle psi over Y to the isomorphism class of its pullback along F. So this is a well-defined map, and it is easily seen to be a semigroup homomorphism. So as a result, we deduce that V is a contravariant functor from vector bundles to abelian semigroups. And since the Grothendieck group is also a functor from abelian semigroups to abelian groups, we deduce that K0 is also a contravariant functor from vector bundles to abelian groups. So they are contravariant functors. By the way, this explains why 0 is the superscript here in contrast to the algebraic K0. So the algebraic K0 is covariant functor on finitely generated projective modules. The topological K functor is contravariant. So 0 is in the superscript here. So this is the main construction of topological K theory, the basic construction of topological K theory. Let's now discuss a relation between topological K0 and algebraic K0, which was defined at the previous lecture. The relation is given by the following fundamental result, which is usually referred to as the Serre-Swan theorem. So again, we assume that X is a compact Hausdorff topological space. Then, first of all, for every vector bundle psi over X, the respective module of sections, gamma of psi, is finitely generated and projective. finitely generated projective C of X module. And second, the resulting functor, gamma, which acts from the category of vector bundles over X to the category of finitely generated projective C of X modules. This category was denoted by FGP at the previous lecture. This functor is an equivalence. An equivalence of categories. Well, this theorem is usually referred to as the Serre-Swan theorem. Actually, this concrete statement is due to Swan. And Serre proved earlier a similar result in the context of algebraic geometry, that is, in the context of algebraic vector bundles over affine algebraic varieties. And this result is a topological analog of Serre's result, and it is due to Swan. So as a corollary, this result implies that we have a natural isomorphisms between V of X and V of C of X. And by applying the Grothendieck group, we deduce that the topological K0 of X is the same as the algebraic K0 of C of X. Well, this is indeed immediate from the Serre-Swan theorem, because these two categories are equivalent, so their semigroups of respective objects are isomorphism classes. Isomorphism classes of their objects are isomorphic, and their Grothendieck groups are also naturally isomorphic. We will now prove this result, the Serre-Swan theorem, modulo two standard lemmas of the theory of vector bundles, which are state without proof. So the first auxiliary result is, this is lemma 1, and actually it holds for an arbitrary topological space, not necessarily compact. So suppose that X is any topological space. Xi is a vector bundle over X. And suppose that E is an idempotent endomorphism of Xi. E is idempotent, that is E squared equals E. Let's look at the kernel of E. So by the kernel of E, we mean the following subset of the total space E. So it consists of all elements V in E, such that E of V is 0. In other words, this is just the union, the set-theoretic union of all kernels of the respective maps over all fibers, of the respective kernels over all fibers. So the lemma states that if we look at this space and restrict the projection P onto this space, then the respective pair, which is clearly a vector quasi-bundle over X, is actually a vector bundle. And it is locally trivial. It is a vector bundle over X. And similarly, we can consider the image of E. The image of E, together with the restriction of P onto this image, is also a vector bundle over X. And finally, these two bundles are compatible with sections in the following sense. The section space of the kernel of E is isomorphic to the kernel of the homomorphism gamma of E, and similarly for the image. Well, I'll not prove this result. It's a standard fact of vector bundle theory. I'll make just some short remarks about how it is proved. To prove the local triviality of this bundle, we fix a point in the base and compare this bundle with the respective trivial bundle of the following form. So the fiber is the kernel of E over a fixed point x0. And it turns out that if we take a suitable little neighborhood of x, then there is a natural homomorphism between the restrictions of these two bundles to a suitable little neighborhood of x. And so it is locally trivial. And to construct such an isomorphism, we have to use the fact that the set of all invertible linear operators on a finite dimensional vector space, specifically on this space, is open in the set of all linear operators on this space, which is, by the way, essentially a Banach algebra result. The group of invertibles of a Banach algebra is open. Part 2 is just equivalent to part 1, because we must replace E by 1 minus E, and the image of E is nothing but the kernel of 1 minus E. And finally, this isomorphism is more or less straightforward from the definition of the kernel. Okay, this is the first result that we need for the proof of the Serre-Swan theorem. And the second result is now specific for compact spaces. Lemma 1 is true for any topological space, but in lemma 2, we require that X is compact. So suppose that X is a compact Hausdorff topological space. Then, for every vector bundle psi over X, we can always find another vector bundle eta over X, such that their witness sum is trivial. Briefly here, the idea is as follows. The proof is divided into two steps. The first step is to construct an epimorphism from a trivial bundle onto Xi. An epimorphism from a trivial bundle onto Xi. So to construct such an epimorphism, we use the assumption that X is compact, and we cover X by finitely many neighborhoods such that the bundle is trivial over each of them. And then by using a suitable partition of unity, we can construct such an epimorphism. And the second step is actually a separate lemma, which says that every epimorphism in the category of vector bundles is in fact a retraction. Or equivalently, every short exact sequence in this category splits. This is also a topological result. Again, it involves suitable partitions of unity. Okay, so now by using these two lemmas, we can now prove the Serre-Swan theorem. First of all, to show that this space of sections is a finitely generated and projective module, we observe that first of all, we use lemma 2. So given psi, we find a bundle eta such that this bundle is trivial. And since it is trivial, this really implies that the respective modulus of sections is free and finitely generated. Well, formally, this is a little and simple exercise, which is more or less, well, some time ago we discussed sections of trivial bundles. So, and from that proposition, it is immediate that the module of sections of a trivial bundle is free and finitely generated. Well, indeed, let me write this down explicitly. Gamma of xv is isomorphic to the space of the module of continuous functions on x with values in v, and v is finite dimensional, so this is isomorphic to c of x to the power n, where n is the dimension of v. So it is free and finitely generated. And since the functor gamma is additive, we have the following isomorphism. And we see that gamma of psi is a direct summand, is isomorphic to a direct summand of a free finitely generated module. And this implies that gamma of psi is finitely generated and projective. And this completes the proof of part 1. Let's now prove part 2. To prove that this functor is an equivalence, we will use the well-known category theoretic fact, which states that if we have a functor, so this is our functor gamma in this setting, so gamma is an equivalence, even only if it has the following two properties. The first will be denoted by 2a. The first property is that this functor is fully faithful. Gamma is fully faithful, which means that it is bijective on morphisms. This means that the respective map between morphisms of vector bundles from psi to eta to the set of C of x module homomorphisms from gamma of psi to gamma of eta is a bijection. So by definition, this means that gamma is fully faithful. This is the first property, and the second property is that gamma has to be essentially surjective. Which means that for every object of the second category, so now this is the category of finitely generated projective C of x modules, we can always find a vector bundle of psi such that P is isomorphic to gamma of psi. So it is surjective up to an isomorphism. Every module is isomorphic to gamma of psi for a suitable psi. So the combination of these two properties is equivalent to the fact that gamma is an equivalence. This is a standard category theoretic fact, which is true for any functor between any two categories. So now we have to prove separately to A and to B. Well, to prove that this map is an isomorphism, we observe. Let's denote this map by star. This map is an isomorphism if both bundles are trivial. This is a simple exercise. Actually, we have already discussed this when we discussed morphisms between trivial bundles. We have a concrete description of morphisms between trivial bundles, and by using this description, we easily deduce that this is an isomorphism. This is a bijection if the bundles are trivial. And applying now lemma 2, every bundle is a direct summon of a trivial bundle, we readily deduce that it is an isomorphism for any pair of vector bundles psi and eta. First of all, by using the fact that psi is a direct summon of a trivial bundle. First, we assume that eta is trivial and psi is not. Then we represent psi as a direct summon of a trivial bundle and use the fact that this functor is additive in the first variable. So the respective map decomposes into a direct sum of two maps. Each of them is an isomorphism, and so the direct sum is also an isomorphism. And then we replace eta by an arbitrary bundle. Now we assume that psi is arbitrary and eta is arbitrary. We represent eta as a direct summon of a trivial bundle. And again, the respective map decomposes into a direct sum of two maps. Each of them is an isomorphism by the previous step, and as a result, the whole map is also an isomorphism. Or more exactly, no, this, just the other way around. This map is decomposed into a direct sum of two maps. It is an isomorphism, and hence each of the summons is an isomorphism. Something like that. The direct sum of two maps is an isomorphism, and hence each of them is an isomorphism. This is the idea. Okay, let's now show that this functor is essentially surjective to B. So we start with a finitely generated projective R module. Here R is the ring of continuous functions on X. We know that P is, every such module is isomorphic to the image of a suitable idempotent endomorphism of a free finitely generated module. You can always find an idempotent endomorphism E of Rn for a suitable n, such that P is isomorphic to the image of E. Now Rn is nothing but the module of sections of a trivial bundle of dimension n. And so we, by using this bijection, we obtain an isomorphism between the ring of endomorphisms of the trivial bundle, theta n, and the ring of endomorphisms of the respective module Rn. This is a bijection, but on the other hand, it's clear that it is a ring homomorphism, so as a result, it's a ring isomorphism. This is a ring isomorphism. So this idempotent eta comes from a unique idempotent in here. E is gamma of F, where F is an idempotent endomorphism of the trivial bundle theta n. Let's now take the image of this. The image of this endomorphism F, and apply lemma 1. By lemma 1, this set, this quasi-bundle, is actually a vector bundle over X. And moreover, applying this formula for F, we deduce that gamma of psi is the image of gamma of f, and gamma of f is E. So this is the image of E. That is, its model is isomorphic to P. And this shows that gamma is essentially surjective. Every projective module comes from a suitable vector bundle. And this completes the proof of the Serre-Sloan theorem. Okay, so that's all I wanted to tell you about relation to vector bundles, to topological K-theory. Let's now come back to algebra. Our next goal will be to give another description of the functor K0 for unital rings. And the respective description will be given in terms of idempotence in matrix rings. K0 in terms of idempotence. Well, at the first glance, the description of K0 that we are going to obtain is probably a little bit artificial, and it looks less natural than our original description in terms of projective finitely generated modules. Nevertheless, this description will be much more concrete, and therefore it turns out to be quite useful in practice. When we want to prove something about K0, it is often useful to interpret it in terms of idempotence. Okay, so again, we start with a ring, R. At this point, R is not necessarily unital. Not necessarily a unital ring. And let's introduce the following notation for the set of all idempotents in R. The set will be denoted like this. This is the set of all idempotent elements of R. We have the following definition. We say that two idempotents, E and F, in R, are algebraically equivalent and we will use the following notation. So little a is for algebraically. Later we will introduce several different equivalence relations for idempotents, and in particular for projections in C-star algebras. And so that's why I put little a here. So we say that they are algebraically equivalent if there are two elements A and B in R such that E equals AB and F equals BA. And in this case, if this is the case, we say that the pair AB implements an algebraic equivalence between E and F. Well, what is not entirely obvious here is that this is indeed an equivalence relation. Well, clearly it is reflexive and symmetric just by construction, but it's not obvious that it is transitive. In fact, it is. And to prove the transitivity, let's introduce the following property. Suppose that we have a pair, AB, which implements an equivalence, algebraic equivalence, between E and F. We say that this pair is reduced. We say that A, B is reduced if it satisfies the following extra conditions, namely EA equals A equals AF, and similarly FB equals B equals BE. Well, let's, before discussing this notion, let's look at the following example, an example and an exercise at the same time, which is actually quite useful because it essentially it gives us a geometric model for algebraic equivalence, and in particular it explains where these notions come from, because of course we can always write these definitions, but at the first glance they are quite unnatural. So let's now understand why they are natural. Suppose that R is a subring of the ring of linear operators on a vector space over an arbitrary field K. So V is a K vector space. Not necessarily finite dimensional, an arbitrary vector space. And of course, the little k is a field. So suppose I have two idempotents, E and F. So they are idempotent operators. And of course, every idempotent operator induces a direct sum decomposition of V into two subspaces. So we can represent V as the direct sum V1 plus V2, and also by another direct sum W1 plus W2, where V1 is the image of E, V2 is the kernel of E, W1 is the image of F, and W2 is the kernel of F. So the exercise is to prove the following. First of all, a pair AB, if we have a pair of elements of our ring, this pair implements an equivalence, implements an algebraic equivalence between E and F, if and only if this pair satisfies the following conditions, which can be represented by the following picture. This is V1, V2, W1, and W2. So first of all, B takes V1 to, well, let's denote this condition by 1.1. So B takes V1 to W1 surjectively. A takes W1 to V1. And if we compose these two maps, that is the restrictions of B to V1 and A to W1, then these maps are inverse to each other. That is, AB restricted to V1 is the identity map of V1, and BA restricted to W1 is the identity map of W1. So this can be represented by the following diagram. So these are the identity maps. So this condition determines the action of B and A on the first pair of direct sums. As for the behavior on V2 and W2, we have the following condition, 1.2. B takes V2 to the kernel of A, and A takes W2 to the kernel of B. So the combination of these two conditions is equivalent to the fact that the pair AB implements an equivalence between E and F. So geometrically, it looks quite understandable, I hope. And which property corresponds to reduced pairs? This is the second part of this exercise. A pair AB implements an equivalence, an algebraic equivalence between E and F, and is reduced if and only if, first of all, it satisfies condition 1.1. So this condition is the same. It satisfies 1.1. And a condition which is stronger than 1.2, namely we require that B take V2 to 0 and A take W2 to 0. Which is again looks quite natural and understandable. So again, these two maps determine bijections isomorphism between V1 and W1, which are inverse to each other, and they act as 0 on the second pair of direct summons. This is a simple exercise in linear algebra, which is more or less immediate from this definition. So these algebraic equations are equivalent to this geometric picture in the case where R consists of endomorphisms of a vector space. So as a corollary, this is part 3 of this exercise. Suppose that R is exactly the ring of linear operators on V. Then E and F are algebraically equivalent, even only if the dimensions of their images are the same. Well, indeed, this follows from part 1, for example, because, well, the implication from left to right is true for any subring in here. So if they are algebraically equivalent, then by looking at this picture, we deduce that these two subspaces are isomorphic. And so of course they have the same dimension. And conversely, if they have the same dimension, we can construct linear operators A and B, which satisfy this condition on V1 and W1. So first we define them on these direct summons, and then we let them be equal to 0 on the second pair of direct summons. And this pair implements an equivalence between our idempotents. Okay, so this is a geometric model of our equivalence, which explains where these definitions come from. We now have the following proposition. I claim that if two idempotents E and F, if they are algebraically equivalent, then we can always find a reduced pair. There is a reduced pair, AB, which implements an equivalence between E and F. The proof is very short. We take any pair which implements an equivalence. Suppose that a pair AB implements an equivalence between E and F. It is not necessarily reduced, so let's try to make it reduced. We define a new pair of elements as follows. We let A prime denote the element EAF. Let B prime denote FBE. Then I claim that this pair still implements an equivalence between E and F. But it is reduced. pair is reduced. This is quite straightforward, so I'll leave this as an exercise for you. This is just a little calculation, just a line. We simply check that A prime B prime equals E, B prime A prime equals F, and if we replace here A by A prime and B by B prime, then we have these two formulas. Moreover, we can define these elements in a slightly different way. And this is also a little exercise, which is quite straightforward. Actually, A prime equals EA, or it is equal to, just the other way around, EA or AF. So we can multiply A by the respective idempotent only on the one side, on the left or on the right, and we get the same element, A prime. And similarly for B prime. B prime equals FB, and it equals BE. So again, the proof is quite straightforward, but the natural question is, where does it come from? And again, the answer is hidden in this diagram. Let's look once again here. If we assume that R is a subring of the ring of linear operators, we have this picture. So we start with any pair, which implements an equivalence between E and F. So it satisfies condition 1.1 and 1.2. So what do we do when we replace this pair by the respective pair A prime, B prime? So this formula, EAF, means that we don't change A on W, but we force it to be 0 on W2. So here it is the same as it was before, and here we force it to be equal to 0. And similarly for B, when we multiply B by E on the right and by F on the left, we do the following. The resulting map is the same on V1, but now we force it to be equal to 0 on V2. And clearly these two maps satisfy these conditions, so they form a reduced pair. So this explains where the proof comes from. And now by using this result, let's call it proposition 1, we can show that this is indeed an equivalence relation. Proposition 2, the algebraic equivalence is indeed an equivalence relation on the set of all idempotents in R. Again, the proof is very short. We use proposition 1, and we construct respective reduced pairs. So we suppose that we have a pair AB, such that AB implements an equivalence between E and F, and is reduced. And similarly, we choose a pair CD, which implements an equivalence between F and, say, G, and such that the pair is reduced. Then, and this is again a little exercise, a short calculation, which shows that the following pair, AC and DB, in this order, implements an equivalence between E and G. Again, this is a little calculation, which is absolutely elementary. Again, let's draw a picture which explains why it is indeed reasonable to check that this pair is exactly what we're looking for. Again, we come back to our geometric model. So we have the direct sum of V1 plus V2. This decomposition corresponds to the idempotent E. We have another direct sum decomposition, W1 and W2, which corresponds to the idempotent F. And we have another decomposition, say U1 and U2, which corresponds to the idempotent G. Well, we have a reduced pair, which AB, which implements an equivalence between E and F, and by this exercise, it is equivalent to a pair of operators A and B, such that their restrictions to the respective subspaces are inverse to each other. So this composition is the identity map, this composition is the identity map, and here they act as zero maps. So they satisfy this condition. Similarly here, this is, I must interchange A and B. This is B, and this is A. And here we have C and D. This is D, restricted to W1, and this is C restricted to U1. And again, these two maps act trivially on W2 and U2 respectively. Then what do we have to do if we want to construct an equivalence between this picture and this picture? We simply compose these maps. So the first map will be AC, first C and then A, and the second one will be the composition of these two maps, first B and then D. That is DB. That's it. So this picture explains where this proof comes from. Okay, so I see we must finish. So let me just finish by an announcement. So without this without an announcement, it will be not clear why do we care about idempotence and about this equivalence relation. So our first goal for the next lecture will be as follows. We replace R. Now we assume that R is unital. We replace R by the ring M infinity of R, which consists of infinite matrices over R, such that all but finitely many entries are zero. So matrices are infinite, but all but finitely many entries of the matrix they are zero. So we are going to show that if we take the set of idempotents in this ring and take the quotient modulo the algebraic equivalence relation, then this is isomorphic to V of R. And therefore, the Grothendieck group of this object, the Grothendieck group of this object is isomorphic to K0 of R. So, я тоже скажу. Formally, it is induced from V of R, but we can also describe it explicitly in terms of projections. So there is a natural semigroup operation here, and the Grothendieck group of this semigroup is isomorphic to K0 of R. Okay, thank you. That's all for today.